Hello Year 12 and welcome to the first video here for continuous probability density functions. To begin with, we're looking at relative frequency as well as reviewing a lot of our stats from Year 11. So we're going to begin by looking at the mean and variance, and I suppose standard deviation, of discrete distributions. Now by discrete, I mean values that are sort of separate from one another, and often we're talking about things that are counted, such as how many rainy days there are in a week during July. So I could have 0 rainy days, or 1 or 2, or up to 7 rainy days. But if I have 3 rainy days or 4 rainy days, there's nothing in between. It's no 3.5 rainy days. It either rains on that day or it doesn't. That makes all of my values, in this case from 0 to 7, makes them discrete. Now, the sum of my probabilities has to add up to 1. Right? This is going to encompass all possible outcomes, that is either 0 rainy days, 1, 2, 3, 4, 5, 6, or 7 rainy days. In any given week in July, I will have either 0, 1, 2, 3, 4, 5, 6 or 7 rainy days, so the total probability has to add to 1. I've got this table here with my values in the top row, that's x, and the probability of that value occurring in the row underneath. So this says I have a 0.1 chance of 0 rainy days, or a 10% chance that there will be no rain during a week in July. I don't have anything there for 7, but I know they have to add up to 1. So if I add up the other probabilities, I can see that I'm sort of falling short by 0.1. They only added to 0.9, so the probability of 7 rainy days must be 0.1 in this example. The mean number of rainy days, right, we can call it the mean with that Greek character mu, or sometimes we call it the expected value, is what I expect typically in the long run to be sort of the average number of rainy days I get in a week in July. And I calculate this in a discrete probability distribution by multiplying each value, the number of rainy days, by the probability of that occurring and adding those together. So it's the sum of x times the probability of x. So 0 times 0.1 is 0, 1 times 0.1 is 0.1, 2 times 0.2 is 0.4, 3 times 0.2 is 0.6, and so on. So I get all of those products, the value multiplied by its probability, then I add those together, and I've got 3.3. That seems reasonable enough. This data suggests that the expected number of rainy days in a week in July is 3.3. Now, keeping in mind this is a discrete, these are discrete values. I can't have 3.3 rainy days, but typically in the long run I have an average of 3.3, or a mean of 3.3 rainy days. Now, it's all well and good to say that I expect to have a mean of 3.3 rainy days, but how reliable is that prediction? Well, it depends on how much variation there is within that data. Okay, is it always 3 or 4? And that could give me a mean of 3.3 perhaps. But in this case, it's spread out from 0 to 7. So we want to determine how much variability there is in this, the reliability of my expectation, of my expected value or mean. And the variance and standard deviation give us a measure of that. So when we calculate the variance, there are 2 ways we can go about it. They both require that previous calculation of mean. Now in one case, we find the expectation of the square of the values. So I square each x value, and then I multiply it by its probability. I add all of those products together, the product of the square of the value and its probability, and from that sum I subtract the square of the mean. That's what these expressions here tell us: the sum of the square of the values multiplied by its probability minus the square of the mean. That's one way to do it, and that's the way that I find mostly to be the most efficient. The other way that we can go about doing this, I'm going to go through some working here. So we take x, my value, in 0, rainy days, square it, would be 0, multiply it by its probability, so 0 squared times 0.1 is 0. 1 squared by 0.1 is 0.1. 2 squared times 0.2 is 0.8. 3 squared times 0.2 is 1.8, and so on. I have all of these products of the square and the probability. I add those together and I get 15.3. That's not the variance. From that 15.3, I have to subtract the square of the mean. So I've got to subtract 3.3 squared from 15.3. And that will give me the variance. The other approach we can take is written here, and from each score I subtract the mean. So 0 minus 3.3, and then I square that and add all of those together. Okay, so the score minus the mean, the square of that difference, multiplied by its probability, and then all of those products added together. Right here. So either way we do that, I find a variance of 4.41, and most typically we're more interested in the standard deviation rather than the variance. The standard deviation is the square root of the variance. So the square root of 4.41 is 2.1. Now, how to interpret that standard deviation we'll go into further throughout this topic, but a greater standard deviation, for now, it's enough to know that that means more variability in our data or in our prediction. A lower reliability of our prediction for a greater standard deviation. Small standard deviation, my prediction is more reliable. Big standard deviation, less reliable. These things are relative. So, now I want to talk about this thing, a cumulative distribution function. And by cumulative, I mean including everything that came before. So, we might use a phrase like up to or no more than. So, what is the probability of no more than 4 rainy days in a week in July? That means I want to know what's the probability of either 0, 1, 2, 3 or 4. It's cumulative, everything up to and including 4. The notation we use for the cumulative distribution function, rather than a lowercase f of x, we usually use an uppercase f of x. And we're firstly going to look at this for a discrete distribution. We're just going to add them up. So the probability of 0 days is 0.1. Of no more than 1 day would include 0 days and 1 day. So that's 0.1 plus 0.1. No more than 2 days would be 0, 1 and 2, those probabilities added together, and so on. I should always find that the big F of x, where x is our last value, right? the cumulative probability of all values has to add up to 1, because that's including everything. The probability that I will have no more than 7 rainy days in July is, of course, 100%. That, I will definitely have up to 7 rainy days. Now, how would I know the probability of the number of rainy days during a week in July? No model is likely to give me a particularly accurate result without observation, right? That I have counted the number of rainy days over many weeks and used that to try to determine the probability that way. We call this thing a relative frequency. Frequency is how many times that occurred. And in this case, I don't mean how many rainy days. I mean how many weeks had no rainy days, how many weeks had 1 rainy day, how many weeks had 2 rainy days, and so on. The number of rainy days is our value. Frequency is how many times that occurred over some number of trials. My frequency is how many times it happened. The relative frequency, well, it's relative to how many weeks I observed. So relative frequency, experimental probability, sometimes we use that phrase for the same thing, and it's the frequency divided by the number of trials. So I noticed here that I did 50 trials, 50 weeks in July. 5 times I had no rainy days, 5 times I had 1 rainy day, 10 times I had 2 rainy days, and so on. My total frequencies add up to 50 because I made 50 observations. So my relative frequency is frequency divided by the number of trials. 5 divided by 50 is 0.1, 10 divided by 50 is 0.2, so on. That gives us our relative frequency, and the sum of those, again, must be equal to 1. So our relative frequency, usually notated here with F and a subscript R, is very much like our probability of X. It's treated in much the same way, except that this has been calculated not theoretically but by observation. And it means that, well, it's subject to some variability in itself, I guess. The more trials I do, the more reliable my relative frequency is as a predictor of the probability. Right, if I do a lot of trials, I get a more accurate result. If I'd only observed the number of rainy days over 4 weeks in July, well, I certainly wouldn't have some relative frequency for all of the different possible values. Right? There are 8 different values that could occur, 0, 1, 2, 3, 4, 5, 6, or 7. That if I only made 4 observations, many of those, if not most of those, would be 0, and that wouldn't be very reliable, perhaps. So they'll add up to 1. Relative frequency is the frequency of some value divided by the sum of all frequencies, or the number of trials. If I calculate the mean and the standard deviation based on relative frequency, we use slightly different language and slightly different notation. Rather than mu for mean, we use an x with a bar above it, and we talk about the sample mean. Rather than a lowercase sigma for standard deviation, I have a lowercase s and call it the sample standard deviation. Okay, still moving along. Here's an example. I'm asked to estimate the mean, the median, the standard deviation for this grouped data. Now this time I have grouped data, and this might be, we're talking about from 0 to 50. Instead of saying now how many rainy days I had, let's say I've got a 50,000 litre tank, or 50 kilolitre rainwater tank. That's pretty big. And at random intervals, I measure how much water is in my tank. I couldn't have less than 0, I couldn't have more than 50. Once it gets to 50, it'll overflow. There's never any more than 50 kilolitres in my tank. There's never any less than 0, can't be less than empty. Notice I'm not counting now. This becomes continuous data. Not all grouped data is continuous, but that example is, and you can see that I go from 0 to 10, 10 to 20. Now, what if it's exactly 10? Well, it shouldn't be able to be exactly 10 kilolitres in my tank. It'd have to be a smidgen more or a smidgen less. Right, I'm going to assume that anyway. So this is how we can take continuous data and treat it as discrete data. So I'm saying that everything falls neatly into one of these categories, one of these classes. So 0 to 10 kilolitres, 10 to 20, 20, 30, 30, 40, 40, 50. But for the sake of my calculations, I need a value, right, to multiply things and whatever else. So I find a class centre. That's just halfway between the bottom and the top of that class. So halfway between 0 and 10 is 5, halfway between 10 and 20 is 15, and so on. I've got a class, but then my class centre is what I'm going to use for my calculations. Right, so you can see there, I've got a class centre of 25 for the class 20 to 30. Now I've got some frequencies here, 5, 12, 38, 26, 19, and when I add those up, I can see that it adds up to 100. So that tells me I must have done 100 measurements of my tank at different points in time. So now I'm going to find the relative frequency of having, so 5 times I found there was between 0 and 10 kilolitres in my tank. So the relative frequency of having 0 to 10 kilolitres in my tank is 5 over 100 or 0.05. Relative frequency of having 10 to 20 kilolitres in my tank, 0.12, 12%. So I work out all my relative frequencies, which is equivalent to my probability, and when I add those up, it should add to 1. Now, to find the mean or expected value, I multiply normally the value by its probability, in this case my class centre times the relative frequency, so 5 by 0.05 is 0.25, 15 times 0.12, and so on. So I find all of those products and then add those together, right? Add that row together, I get 29.2. So that's telling me that at any particular point in time, right, if I randomly test my tank, generally I could expect to have 29.2 kilolitres of water in there. That's not always going to be the case, but that's my expected value or mean value. Now I'm asked to find the median, right? And this is a little bit different. So typically when we're finding the median, or for that matter quartiles, deciles, percentiles, very often we draw a cumulative frequency histogram, draw a line graph on that, we call an ogive, and I determine this graphically. It works quite well with grouped data. We're going to do this algebraically. It's a little bit fiddly. It's not a question I think I have ever seen in an exam. I'd be surprised if you had to work it out, but nonetheless, follow it along. You never know what's going to happen. It's not that hard. It just requires you to stop and think about it a little bit. So, if I took 100 measurements, then we could say 50 of those measurements are in the bottom half, and 50 of the measurements were in the top half. And the median is the number exactly between the 50th and the 51st observation when they're ranked from smallest to largest. So I want to find what the, typically what the 50th and 51st observation is. And let's have a look and see, and we're going to find what value sits between the 50th and the 51st. So, I'm going to find the cumulative relative frequency. So you can see I start with the 0.05 and then I add the 0.12 onto that, add the 0.38 and so on. And of course at the end I end up with 1. So the halfway point is at 0.5. Now where is 0.5? Well, the first 5% of scores were between 0 and 10. The first 17% of scores were between 0 and 20. Now the first 55% of scores were between 20 and 30. That means the point where 0.5 occurs is somewhere in this class, the 20 to 30 class. So the first, if you like, 17 out of 100 scores finished at around 20, and then the 18th till 55th are in the 20 to 30 range. So somewhere between 20 and 30. I could say 25 is in the middle, but from 17 to 55, they're all somewhere in the 20 to 30, and I'm looking for something probably closer to 30 than 20. Okay, because 50 is closer to 55 than it is to 17. So we just break that up proportionally. By that I mean, I want to go from 17 to 50. Right, that's how far I want to go from the bottom of my range to the 50% mark. And I want that as a proportion of, if you like, the width of that class, which is from 0.17 to 0.55. So, where I want to go, right, how far I need to go to get to my 0.5, divided by how many, or how much of my frequency, my relative frequency, is within that band. Right, I find that proportion. I multiply it by the values contained in that band. So from 30 to 20, there are 10 values, if you like, 20, 21, 22, 23, or 10 kiloliters that it could be in that 20 to 30 range. That tells me how many kiloliters then I am above the start of my band, the 20 kiloliter mark. So I add the starting point 20 onto that as well. So that gives me a median of 29. As I said, that's an unusual kind of a thing. Normally we do that with a graph. I didn't really feel like drawing a graph here, and it didn't ask me to. And so we've calculated it that way, and you see that it is certainly much closer to 30 than it is to 20, because my 50% mark is much closer to the top of that band than the bottom, closer to 55 than 17. Anyway, that was the median. Now we've got to find the standard deviation. I can't find the standard deviation without finding the variance. So I'm going to use this first method I described to find the variance, square my values, or in this case the class center, multiply it by the relative frequency. Okay, so 5 squared times 0.05 is 1.25. 15 squared times 0.12 is 27. I do all of those, add them up, and I get 969. Remember, that's not your variance. I still need to subtract the square of the mean. Right, the mean was 29.2, so 969 minus 29.2 squared is 116.36 is my variance. Now from the variance, to find the square root, find the standard deviation, all I have to do is take the square root. So that's 10.8, my standard deviation. So a mean of 29.2 with a standard deviation of 10.8. We've now done the 3 things asked of us in that question. We found the mean, the median, and the standard deviation, but of course you had to find the variance as well. Let's just go over those things. The sum of all probabilities has to be equal to 1. The mean or expected value we find by multiplying each value with its probability and adding those together. Variance can be calculated two ways, and I would rather square the value, multiply it by its probability, add those together, and subtract the square of the mean. But you could subtract the mean from each value before squaring, multiplying by the probability, and adding those together as well. Standard deviation, last thing to remember, is square root of variance. Righto, that's the first video. I know it was pretty long. Next video is on continuous distributions. We're going to treat those differently to these discrete distributions, but they do have a lot in common. Any questions? Hit me up. See you in class.